I want to talk to you today about my team's journey from taking an application from being hosted on bare metal Windows to up in the cloud in Kubernetes in a grand total of 2 months. Just a little bit about myself to start off with. My name's Paul. I'm a software engineer at SAP. We're a consulting firm based out of Carmel, where we try to increase our clients' value through the software we provide. I graduated from Purdue University in spring of 2017, and I have a blog. I don't post a lot there, but some stuff is up there if you feel like checking it out. When you're making a new application accessible in the cloud, things seem kind of easy. You just follow all the tutorials, you deploy to Heroku, just little bird going out up there. But for those of us who have worked with legacy applications, things are a little harder. The decisions that you made 10, 15 years ago, they don't really scale in the cloud. And it seems that it may take a whole army to slay that dragon. So you might even have wizards involved. I want to talk to you today about what our team did to overcome that dragon, and then hopefully elaborate on some of the gotchas that we found along the way. So if you're going through a similar process, you can save some time making the mistakes that we made. To start off, I want to talk about the application itself. It was incident tracking software. So let's say you're working in the warehouse and you get injured. Then someone goes into the software and files a report. The managers can see it, can get a bunch of metrics out of it. On the technical side, it was a C# application hosted on Microsoft's IaaS. And this was an application designed to run on a bare metal machine, single tenant. Why would you ever need to carry about multiple companies when they're going to run it on their own computer? That's just a waste of time. And it was 10 to 15 years old. So the functionality that it had at the moment wasn't exactly the functionality that it was intended to have at the offset. Some key architectural choices that were made. Again, ASP.NET on a bare metal machine, talk to a SQL server, all that's pretty mundane, but they had a series of these 3 helper tasks to supplement the application. 1, handling the background running, keeping the state of the database up to snuff and the application state. They had email alerts, so someone gets hurt, maybe their boss is notified. And then they also retroactively added a search feature, so they needed to start indexing some of this. And instead of putting that in the application, they found an off-the-shelf solution that they could just install in Windows and everything would be great. On to how the app was developed. There were 2 main teams that worked on this. There was one team in Indianapolis, an SCP team, and then a client team that was several states away. They were focused solely on development. They would get a feature request, they'd work on it, they'd test it for sure. But when it came time to deploy, they handed it over and let the ops team handle that. And at most, they would hear, hey, this feature doesn't work, or we'd like a new request. They wouldn't hear the struggles it took to deploy it. So they never had the desire, or frankly, the budget to move over into this new DevOps world. They used Jenkins for a lot of their automation, and as Jenkins tends to get, it was old and plugins were unmaintained. Worse than that, though, only one team had access to the Jenkins instance. So one team could push their code up to Jenkins and have it build and get results from the tests. And they could see that before they merged in their PR. But the other team didn't have the luxury. They just committed code and would maybe get a Slack message the next day that they broke something. All of this was amplified when it came to deploy. When they had a release branch, the team that had access to Jenkins would hit the build button. They'd wait for Jenkins to tell them to go or no go. Then they'd hand it off to the other dev team and be, OK, we're ready to deploy. This dev team would then manually build the binaries and write the instructions for any breaking changes for this application. They wouldn't deploy it themselves, though. They'd again hand it off to the ops team, who would then have to follow those instructions, sometimes multiple pages, to deploy the application to all of the servers. This involved manual file drops, just take down the server, copy and paste, bring it back up. And of course, nothing ever went wrong in this scenario. Well, that's why things went wrong all the time. Further amplifying this, there was no automated database creation. They just kind of generally knew what the schema should look like and copy bits from other databases and delete data if they had to stand up a new client. So what problems did this cause? There was a general uncertainty on the state of the code. No one really knew if what was on the master branch was deployable or had features or bugs in it. And then when it came time to QA, the QA team would ask for a build we put on a server so they could verify it before releasing. And it wouldn't be days or weeks for the ops team to acknowledge the response or the request, but it would take days or weeks for them to spin up a server, debug all the common issues that they normally had, and then let QA team know that they could access it. And then QA did as they do, and they found issues, so they'd tell the feature team, hey, we need this fixed. This part's broken. Wait another couple days or weeks, get the feature fixed, and you get to start all over again. Take a couple months to get something through QA and deployed. Finally, this all accumulated in the fact that there was one release, they just deployed the entire wrong version of the application. There were features that they promised that weren't there, and bug fixes that hadn't been made in. So that's where we came in. They experienced the pain of not having a DevOps solution, and they found the budget, as they do, to move to the cloud. They had other areas of the business in Azure, so that was where they wanted to keep this new part. And they wanted a full CI/CD pipeline that both teams could access, which included push-button deployments so that the ops team didn't have to follow a list of manual instructions. They wanted to experiment with some new technologies like Docker and Kubernetes. And I spoke earlier this morning about when you shouldn't use Kubernetes, and some of my alarms were ringing in my head. But they had a compelling case that if they could prove it out with this application, they could bring it to other areas of the business. And they were certainly at the scale where that seemed feasible. So we said we'd give it our best shot. There's a team of 3 that worked on this. 2 of us were fresh off a different project, not having worked on the application. And then the 3rd member was on one of the feature teams, so he was able to help keep us in check with what the application needed to do. And we did all of that in 2 months. The concrete goals were to, A, containerize the application. Even if we couldn't get to Kubernetes, we wanted to be Dockerized. We wanted to fix the database deployment problem by automating that. We needed to set up Jenkins in the cloud. And we knew with our timeline of 2 months, we weren't going to be able to go all the way through to production. So we wanted to solve the problem that the QA testers had and at least allow them to have push-button deployments into their test environment. And all this said, should all be scripted so that it's reproducible. So starting off with containerizing the application. This was a C# legacy ASP.NET application, which meant no .NET Core. We didn't have the time to change that, so that meant we couldn't use Linux containers. We had to resort to the spooky Windows container. Frightening, I know. So this is where we have to get into some of the nitty-gritties of containers. Usually you can kind of just be like, oh, they don't have a guest operating system, and that works. The selling point, from my understanding with containers, was that they share kernel space, and that's what allows them to not have their own operating system. In Linux, there are very few compatibility problems if you attempt to use a newer kernel feature, simply because it just meshes better. So when you run a container on Linux, and you try to use some new feature like that, it's a runtime problem. It's so rare that they let you spin up the container, and more likely than not, you're not going to run into an issue. On Windows, there's a whole slew of compatibility problems, so they won't even let you start the container if your kernels don't match. They just say, nope, I'm not going to even try. They give up. So Microsoft provides this super handy chart of compatibility. And it's probably a little hard to read up there, but the key things to note are if your container operating system, the operating system that it's based off, is newer than the host machine you're going to run it on, there is no support. It's like half the chart. It's not possible. Then, if your host operating system is newer than the container that you base it off of, they offer this thing called Hyper-V isolation. It sounds kind of weird. I thought we were dealing with containers, Hyper-Vs for virtual machines. So we were a little confused, but we kept going. Key to note, if they match exactly, that's where you get to use process isolation, which we became intimately familiar with. The difference between these two, this chart, also provided by Microsoft, shows on the far left what your typical process will look like when just running it on a computer. Your processes, whether they're on Linux or Windows, run directly on the kernel of the host operating machine, and it's very fast and efficient. And then one step to the right, you have what we traditionally think of containers, where they're a little slower and a little less efficient, but they still share the kernel, so you still get a lot of the benefits. Then on the far right, we have virtual machines, as we know and love them. They're more isolated, more secure, but not nearly as quick. And then in between those two, you notice there's no equivalent in Linux, but in Windows, there's this Hyper-V container. The thing that's missing in that portion of the diagram is the shared kernel space. Hyper-V containers do not share the kernel. What Windows will do is spin up a virtual machine to run your container on, and all of the fun nuances that come with that. None of this was obvious to us setting out. We were traditionally working with Linux containers. So we take a look at that chart and say, well, let's just base our container off of Windows Server 2016. It's compatible everywhere. What could go wrong? We'll see what goes wrong. Now that we had picked our base image, it was time to decide how we wanted to kind of architect the Docker container for this application. Typically, when you're making containers, you want to run one process per container. And that would work well. We could run our ASP.NET application alongside IAS. And that was great. But we also had these background services that had to interact with the application. We could put them all in their own container, as would best practice recommends, or we could shove them all into one container, this giant monolith, if you will, which is what we chose, simply for the sake of time. The services were expectant of being on the same machine as the legacy application, and we weren't entirely sure what orchestration tool we were going with, so we just wanted to make something work, regardless if it was on Kubernetes or just being run with Docker. So on to the fundamental problems that we had with the application. Now that we decided the base image and we've picked what our container is going to look like, both the application and the helper services and IAS itself, they all had these various flat files of configurations that no one really knew what was involved in it because they weren't in source control. So when we rolled onto the project to start developing, we're like, how do we get the app set up? Oh, you download it, and then you install dependencies and run it. Well, I got an error. Oh, yeah, well, you have to make this file and put this value in it. Repeat that until we finally have the application up. And that was for, again, all of these services, not just the main application. So it's no wonder that ops had a hard time setting up new servers because even the developers don't know what's going on. So that was the first thing we wanted to tackle. We consolidated the configurations. One of the benefits we got by putting all of those background services in the same container is now their locations on file system were static, so they didn't have to be configured anymore, so we could just hard code those values because they were constant. We got, at that point, maybe 10 or 15 configurations we still had, and we couldn't re-architect the application due to time constraints, so we templated the configurations. And then when we started the container, it read in from environment variables, those configurations, filled in the templates, and put them in the right location every single time. And with those templates, now that they had the crucial configuration pieces out of them, we could put those in source control, and they could go through all the rigor that the code went through, and code review, documentation, and stuff like that. Great. So we've containerized the application. Now on to the automated database creation. Like I said earlier, this was a Microsoft SQL server. There was no real clean way to set it up. Again, there just wasn't. The Matter version 7 that we were on introduced proper application migrations, which is a great win. So we really needed to just get our scripts up to that 0.7 version, at what point the app could take over. Again, due to time constraints, we couldn't fix the application migrations to just make them proper and go from scratch. And we wanted to support both Azure SQL databases as well as a Dockerized database. One we'd be running in our test environments, which would look more like in production, because we wanted this to be usable with minimal extensions to get into production. But then for things like our integrations tests that ran on Jenkins, we wanted a container that we could spin up to save costs. Luckily, there was a way forward. We managed to find these test scripts that QA had used to get the databases up to snuff. They had one script to get to the major version, and then 7 other scripts for each minor version. So a total of 8 scripts in total. It looked something kind of just like that. I don't know if it's hard to see, but it was basically upgrade the schema, add some test data. Upgrade the schema, add some test data. So we thought, we'll just add a conditional. Only if I want to see the test data, will that information get added? We weren't so lucky because the scripts were written in a way that, although their names said this one deals with the schema and this one deals with adding data, some of the schema upgrades relied on data that existed in the other set of scripts. So we had to manually go through and untangle that and move the right commands that address the schema into their own files. So it took longer than we wanted, but we got there. We had the ability to create a database from scratch with and without test data, which is what our QA team needed. It's fairly easy. Now on to Jenkins. We were crunching for time, so we looked out that Microsoft provided a solution template on the Azure Marketplace with all the basics that you really need for a Jenkins instance in the cloud. We wanted some control over what machines, virtual machines, were running our Jenkins master and the build agents, so we used Packer to automate those image creations with all the tools that we needed. And that graphic up there shows a lot of different tools that the solution template provided, but we mainly took advantage of on-demand build agents and the artifact storage. Now, this was important because we knew we're not going to get into production right away, so we wanted some central place where we could build the binary just like normal, put it in blob storage, and then when someone needed to deploy it, they had a high degree of confidence they were deploying the right application. Who's here familiar with Jenkins? Good portion. For any of us that aren't, it's really just there's a master machine that offloads builds to other machines to do the actual work. In the old days, this was a physical machine. In our new world in the cloud, we have a couple options. We can have virtual machines be our build agents, or we could even use containers themselves. So with the virtual machines, you had a little more fine-grained control over what exactly was in the image. You got to pick how much CPU it had, how much memory it had. But it was more to manage, and they're slower to spin up than containers. That's kind of why we containerize things nowadays. And frankly, they cost more. With containers, they're fast to spin up, and we were toying with the idea of going into Kubernetes, which Jenkins plays really nicely with. So we thought, you know, container build agents sound like the clear choice that we want to go with. We chose virtual machines? That doesn't make sense. Why is that? The build agents needed to build Windows Docker containers. And you need Docker and Docker support to do so. Here's a nice image of the PR that we found with the Docker library, where they said, we talked to the Windows team, they're not going to support it, We have no way forward. So it wasn't possible. We could have done some magic with the Docker socket, but that's kind of frowned upon, and we wanted to just do things the right way. So anyway, we had picked virtual machine build agents instead of containers because we were forced to. On to Jenkins pipelines themselves. Before, they did not have CI builds for any of their feature branches. So before they merged, they had no confidence if tests were passing or not. So we thought, hey, we'll give them a multi-branch job where every branch that gets pushed can go through the build process. Stages were fairly minimal. You just build the application on the virtual machine and then put it off in blob storage if that was like a release candidate or something. The application would be unit tested, and then we'd finally build our Docker image. Typically, you'd want to build the application in a Docker file, but with needing that binary, it just would have been duplicated effort. So then finally, that container would go into Azure's container registry, which is just a nice place to store containers. And that was the main CI build that we were focused on. There was also the database creation task that we needed to make. Again, we needed to support two things, an actual Azure SQL database and a container. So we'd either build that container. Microsoft provided some very nice base images with minimal configuration that we had to do. Or we would go out to Azure and make the correct calls to spin up that SQL server. And in either scenario, if we wanted data to be seeded, that would be done. And so the containers would be put in the registry, or we would have a SQL database. They also had integration tests, which they referred to as system tests, which we only wanted to run on the master branch since they were a lot slower than a lot of the unit tests, and their costs were a concern. They were kind of tricky to modify to work in this new containerized world this application was living in. These tests, they were just Selenium tests, but they cheated a little bit. So after they went through the web page to do some things, they would also go create a file on the file system and expect the application to handle that. So we would spin up our application in our Docker container that we created and then run the Selenium tests on the build agent. And so that same paradigm didn't work any longer. So we had to modify those. And then finally, we made a deployment job where all it did was take the container that we had already vetted from the container registry and deploy it to, well, we haven't talked about that yet. So it's going to deploy it somewhere. We're going to get there. So the last thing we had to do was make the push button deployment into our test environment. So again, I want to stress that this application was single tenant. So for every user of this application or company that used it, we needed a separate container. I talked earlier that you don't want to use Kubernetes for an application, but this was almost like 20 to 30 different applitions because they all had to run separately in their own containers and own databases. So we're on Azure, so let's use Azure's Managed Container Service, AKS. Well, they don't support Windows containers as part of that. The Microsoft provided tool, we thought that was a surefire win, but it was not. It was better than AWS or Google Cloud, which don't support Windows containers in general. Some of Azure's other services do. So we had a couple options. We could have used Virtual Kubelet, which at the end of the day kind of translates API calls made by Kubernetes into other services like Azure's Container Service. Or we also could have used this tool called ACS Engine. An ACS Engine essentially created ARM templates which mimicked how ACS works. It would provision virtual machines that would run your cluster. Luckily for us, it allowed creating Kubernetes instances. It also supported Swarm at the time. But the big win was that it supported the hybrid cluster that we needed. We needed our master node to be Linux to run all of the things that Kubernetes needs to run, but we needed the nodes where the application was running to run on Windows Server. Now, I would recommend this tool, but they deprecated it and switched over to what they call AKS Engine, which is really all the same stuff, but they took out the Docker Swarm and other orchestrators. Now you can only use this tool with Kubernetes, if that tells you anything about the state of container orchestration. We were able to put our configuration files that we put into ACS Engine and source control to keep everything automated. So our Kubernetes instance itself. Talked earlier, we had the master node, which ran on Linux. It also ran our Nginx ingress controller and assert manager instance, which suffice to say it handled all of our network load balancing and creating TLS certs for security. And then all of our other application nodes were Windows Server. And with this application being the monolith that it was, it took a fair bit of resources. And the virtual machine choice that we made, we could fit 4 applications per worker node. And a really nice feature that ACS provided for us was, let's say we had 8 of these applications currently up, so that meant we had 2 Kubernetes worker nodes, and we want to spin up a 9th. Kubernetes would start complaining, I don't have enough resources, and the virtual machines generated by ACS Engine would acknowledge that and provision a new node for Kubernetes to run off of. And then, conversely, if we only had 3, it would scale down our backing nodes to match. Cool, so we've containerized the application, we've automated database creation, set up Jenkins, and have push-button deployment. So we're done, aren't we? We're not. The performance was absolutely pitiful. When you're dealing with Linux containers, you're looking at pulling maybe 40, 50, maybe 100 megabytes for your base layers. The base layers for Windows Server 2016 containers were on the orders of 4 gigabytes, 6 gigabytes. So it took a lot of time just to download them, and we were doing that every CI build that we had. Furthermore, when we were building the Docker containers, every stage seemed to hang for like 30 seconds. It should just go really fast, but it wasn't. And our system tests were failing inconsistently and really slow. We wanted our main CI build to be less than 10 minutes, and it was taking 30 of that to build the application that, when running on your local machine, took maybe 2 or 3. And then we wanted our system test to be in under an hour, but it was 5.5. We were far from done. So there were a couple quick fixes that we did to remedy some of the problems that we saw. With those large base images, since we had utilized Packer earlier on in the process, we just added another step where we pulled the base layers. And that added time to creating those Jenkins build agent images. But 1 time every couple of weeks is a lot better than 8 times a day. And then we parallelized the system tests. Since they were Selenium and we had modified them to a certain point where they could run on Jenkins, we could just spin up 5 more virtual machines to run the application, and then distribute the tests among those nodes. We went with 5 just because of budget constraints. We could have done more to get more parallelization, but we were cost conscious. But there was a larger problem still at works. For some reason, the build still took forever of the Docker container when all it was doing was copying binaries. And I want to go back to that isolation level that we talked about with Windows containers. We were using Hyper-V isolation and not process isolation. If you see on this chart, that's on the wrong side of fast and efficient. So we were here. We used 2016 container operating system versions, but we had used Windows Server 1803 because 2019 was not an option at the time for our Jenkins builds, because whatever, it would work, and they're faster and better and have all the new stuff. This is all internal. We don't care. So we kind of went the wrong direction at first. We took our Jenkins build agents to be Windows Server 2016 images, where things got kind of dicey. Our virtual machines were taking now 20 minutes to spin up instead of 5. We did fix the container start time, or the build time rather. Instead of taking 5 minutes and hanging on all these Docker stages, it went lickety-split. But we kind of made negative progress from where we were before. We were sitting at 30 minutes for our CI build time, and we went up to 36, which is close to where we started. The system tests were still flaky, and as we dug more into it, because we thought, well, we changed the base image, like everything should work now. We're using process isolation, it's a real container. There was this inexplicable time skew on these Windows Server 2016 containers that try as we might to sync with an NTP server or heck, just manually force it to a certain time, it was always 30 minutes off. We never got around that. So the solution we derived upon was upgrading all of our images to the latest and greatest. But we still needed to use process isolation. So we were on Windows Server 2016 for both, and then we moved to Windows Server 1803. While the spin-up times for the virtual machines were better with these 1803 Windows Server versions, 7 minutes still just didn't feel right when we were basically building constantly throughout the day. The team was pushing enough code that these virtual machines were almost always up, so we bit the bullet and decided to keep our build agents around for an hour. So how it turned out is the first person to make a commit in the morning would wait an extra 7 minutes, and then everything would be fast for the rest of the day until they spun down at like 6 o'clock in the evening. So this is the pipeline that we ended up on. At worst case, our CI builds took 16 minutes. In the best case, they were 8, which was under that 10 that we desired. And our system tests weren't under an hour, but they were close enough that we were going to call victory on that. So after 2 months, we had successful system tests, VM agents in the cloud to build our code. Our CI builds were fast. They weren't as fast as they were on bare metal, but they were also accessible by the whole team, and we had push-button deployment to Kubernetes. Before, the process that was involved took months to get things deployed. There were multiple handoffs with teams that didn't necessarily work together. They were siloed, months to deploy. And after using some cloud technologies, Kubernetes, Jenkins, containers, we were able to get those months to deploy down to hours, where all teams could work in the code base and get feedback. So all of that said, the key takeaways that we had from this project were that the tooling for Windows containers is lacking, certainly compared to Linux containers. I would personally go so far as to say if you're not using 1803, it's not even worth trying. You're going to encounter bugs that are showstoppers, where automation could have gotten you a lot further. The importance of scripting, all of this, the number of times that we had to take down Jenkins and stand it up from scratch was higher than I'd like to admit. But the fact that we spent the extra time in the beginning to automate that meant that instead of taking another 2 months to spin up and iterate, it took us 2 hours. And then finally, that cloud costs should be monitored. We could have had 20 virtual machines running our system tests, and we've gotten really fast feedback, but the business might have gone under too, which won't have anything to test at that point. So I want to ask if there are any questions. Yes?
So that last point, how did you monitor the costs?
So
can you repeat the question?
Yes, so how did we monitor the cloud costs? Azure was really nice about this in that regard. We were on their dashboard pretty frequently throughout the development process, and one of the widgets they offer is literally it's an estimated cost. It'll show you, okay, you're on the 5th day of this billing cycle, and you've spent $200. You're probably going to spend a couple thousand at the end, at which point we're like, oh crap, let's deprovision some stuff. So whenever we'd log in, we'd constantly be reminded. So just increased visibility, more or less.
Azure offers an extra cloud cost monitoring widget that apparently actually costs money to run on a daily basis. Did you enable that, or did you use just the base model?
We used the base model. It worked for our needs. Everything was separated from other areas of the business, so it was very clear with tagging what resources were ours and what we could clean up. Yes? Absolutely. They, the client was very concerned about the ability to tear everything out of the cloud at any moment and run it on bare metal again. And we had a fair amount of Jenkins experience, so we maybe a little overconfident in that regard. We probably could have saved some time. I'm also not aware of what services offer the Windows Server builds. You said Azure DevOps, and I had a flashback to the first meeting where we went to the client and Bob was like, "Let's use Azure DevOps," and they said no. So that's yeah. It was before we really got into the process. It probably would have been a better solution. I would probably say a mix. They were very confident that they wanted to use these technologies, and maybe we did a poor job of explaining why that wasn't the best option. But that's a good call out. Right, there are managed solutions like Azure DevOps and VSTS that Circle CI, yes, that provide that. Any other questions?
So
yes.
in the end, would it have been faster just to rewrite the application into something that would run on Linux?
There were several days, like 5 p.m., that were like, okay, let's just rewrite it. Yeah, let's get .NET Core running. There were a couple key libraries for features that were real selling points that were based on libraries that just weren't updated anymore. So there was no like migration path to .NET Core or something. It's definitely, if that's the option, I would heartily recommend going to .NET Core, getting on Linux, taking advantage of all the managed services that exist. Yeah.
When you mentioned the parallel runs and kind of cutting them back to just 5 versus more because of cost, did you have to find a point of diminishing returns? Was it like a hunch, or did you actually kind of calculate?
That's a good point. There was about 15 of those minutes were just kind of static. It's setting up the virtual machine and then getting the container running. So it was more of a gut feel. We tried 10, we tried 2, and it was just more like we wanted to hit that hour mark, but we had a predefined budget that we could work on, and so it was like we want to spend that in other areas because the Kubernetes cluster also had 3 virtual machines, and so 5 was kind of the sweet point where we have enough budget for everything else, but also the speed up that we got. Keep
Sorry,
going. Yeah.
I got lots of questions. Would it have been possible to do something with like file system snapshotting to help reduce that cost of taking images and rebuilding them and putting them back up again, or is that already kind of baked in here?
It may have. The number of times that we had to rebuild, like you're talking about the build agent images, that was never necessarily automated. The process was automated, but it was never like, Jenkins never did that. So we did it a lot in the beginning, and then we did it maybe one time in the last month. So the build time was only an hour to get those images created, so I don't know how much gains we would have gotten from snapshots in our scenario.